guys, it's time for another episode of Physics in the Flesh, Electric Potential and Electric Potential Energy 2. A simple model of a hydrogen atom shows the electron and proton as point charges separated by a distance of 4.99 times 10 to the minus 11 meters. Calculate how much work is required to break apart these two charges and to separate them by a very large distance when the electron is initially at rest. So, the work required to overcome and to separate these two is equal to the change in energy, the amount of energy that must be altered from one form into another. Now, usually with these types of problems where you have charges, we're dealing with kinetic and electric potential. Now, we're told that the electron is initially at rest to give us an idea that the kinetic energy may be zero, but you must also consider the proton. Okay, now remember the very simple model of the atom is that you've got your protons in the middle, you have your neutrons, and then you've got your electrons orbiting. I mean, this is the very simple Bohr model, right? I mean, even in the complex model, the same principle applies. You've got electrons orbiting around the nucleus, which is positively charged. So for all intents and purposes, the proton is stuck in the nucleus. We can assume that the initial speed of the proton is also zero, which means the initial energy, there's no kinetic component to it. It's purely electric potential. So we can say that work is equal to the change in electric potential energy. Now, like I said back in video 163, change in electric potential energy is just simply the final electric potential energy minus the initial electric potential energy, EE2 minus EE1. We saw that the formula for electric potential energy is K Q1 Q2 over R. So in this case, R2 minus K Q1 Q2 over R1. Now, before I go ahead and just factor it out, take a look at this. I'm told that, okay, so they want to be separated by a distance of 4.99 times 10 to the minus 11 meters. Well, this is how much they're currently separated by. So this would be our R1. But we want to separate them by a very large distance. Now, whenever you hear something like that, a very large distance in these electric problems, you have to assume that R is becoming really big, it's becoming infinitely large. And even though the electric force doesn't necessarily go to zero if R gets very big, it gets close to zero, it doesn't actually hit zero. But in the scenario where we consider R approaching infinity, this is like a limit, the limits we encounter in calculus. If R approaches infinity, the electric potential energy approaches zero. So therefore, if R2 goes to infinity, this whole expression goes to zero. Okay, so this thing disappears, which means my work is simply minus KQ1 Q2 over R1. Okay, so now at this point, I just have to plug in my values. So minus my K is the same, 8.99 times 10 to the 9. Newton meters squared per coulomb squared, Q1. Now, we're not told the charges in the question, but we are told it's an electron and a proton, and you know the charges for those two. You should have them memorized. For a proton, it's 1.602 times 10 to the minus 19 coulombs, and an electron has the same charge, just opposite sign. So minus 1.602 times 10 to the minus 19 coulombs. And we divide that by the distance 4.99 times 10 to the minus 11 meters. So just crunch that in your calculator and you should get that your work is equal to minus 4.6 times 10 to the minus 18 joules. And that's it, guys. I hope you enjoyed the video. Be sure to smash that like button if you did, and subscribe to Physics in the Flesh. I will be posting a new video tomorrow at 12 noon. Video 166, the Millikan Oil Drop Experiment 1. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Whoop, whoop. Holy crap, my nose looks big on camera. I gotta find a new